to review that. So basically review the basics of TensorFlow and the other libraries that we'll be using. And then also we'll start looking into classification. Last week we looked at regression, so naturally this week we'll look at classification. So yeah. A little bit about last workshop. So we do know that it did not go as well as planned, primarily just because of the room size. Like we had over 100 people come out and 4760 could not accommodate that. We were able to get this room, which is a little bit bigger. And then in terms of feedback, we did notice that people are kind of varied on the speed of teaching and the content in terms of some people said it was too advanced, some people said it was too slow, which is totally understandable because we're kind of a community where we do want to welcome people of all sorts of different experience levels. So that was kind of expected. And what we've done in this workshop to kind of mitigate that a little bit is two things. So basically, we're going to be trying like a live coding approach for people who want a more interactive, hands-on session. And through doing that, we basically hope like actually getting your hands dirty and writing some TensorFlow code is going to be helpful. So yeah. And then a quick update on the research paper reading group. So we did put out an application, and if you haven't gotten a chance to sign up, we'll send you that link again. We'll post it on our Facebook group. But tomorrow is the due date, and after that, we'll basically be contacting everyone who signed up and kind of discussing our plans for this research paper reading group. So what we're planning to do is meet either weekly or bi-weekly, basically however often people want to, and discuss a machine learning paper. And kind of the knowledge there that we'd like to have for a solid discussion is like basically understanding the basics of machine learning. So like if you've taken the Coursera course online, or if you're currently enrolled in a machine learning course, then you should probably be good. But yeah, I think that's it for logistics stuff. So now I'm going to let Adi review what we covered last week.
Awesome. Okay. So if you were here last week, you know that we went over linear regression, which is probably the simplest model in all of machine learning. And if you weren't here, just to get a little bit of overview on what machine learning is, you can think of machine learning as this idea of us learning a function that maps inputs to outputs based on the training data that you provided. Right? So basically what we learned last time, we had an overview of what machine learning is, and then we also looked at some quick Python reviews. So that's the programming language of choice when using TensorFlow. So if you have experience with other programming languages, that's totally cool. That's definitely helpful. It's just that Python has a little bit of a different syntax to it. So if you need a Python refresher, then the slides in the previous week will be helpful. And then so we also talked about supervised learning. So within the field of machine learning, you have 3 different components, right? You have supervised learning, unsupervised learning, and reinforcement learning. So the idea of supervised learning is that you have this labeled data set from which you're able to learn the function that maps inputs to outputs. And so the first function that we learned is the y equals wx plus b function, or commonly known as linear regression. And so we talked about things like weight matrices, loss functions, and gradient descent. And then finally we also looked at some basic TensorFlow concepts. So just to kind of review what linear regression is, it's one of the simplest models in machine learning. So basically you have 4 different components, right?
I'm sorry, where can I get the PDF for this?
So we have the slides on the event page.
So if you go on Facebook and you go to the event page,
Yeah.
you should be able to see the slides there, and it'll take you right to this link.
And if you want the slides for last week, then it's on the last week's event.
Okay,
Yeah.
thanks, appreciate it.
Yeah. Yeah, so we have linear regression, right? It's one of the simplest models in ML. So it's basically composed of 4 different components. It's composed of your outputs, your weight matrix, and your inputs and your bias term, right? And so your outputs are going to be a linear function of the inputs. And so last time we talked about this particular problem space, right? We wanted to, given data about houses and the prices that they sold for, we wanted to predict the price of another house. And so we talked about how to represent this data as features, and we talked about how to take a machine learning approach to it, which is we want to create this function that takes in these inputs, so it takes in the information about the house, and be able to output a price prediction for what the model thinks that the price should be. And we want this price prediction to be very close to the actual value. So this is kind of like a high-level approach of what we're trying to do with machine learning. So just to kind of overview, we want to first figure out what our problem space is. We want to determine how to represent that data. So if you remember what the problem space was, we want to be able to represent the data of the training set. So the bedrooms, the square footage, the neighborhood, all in a vector format. Right? So once we have that data representation, then we can go about initializing our weight matrices and bias terms, and then taking each training example, feeding it into the model to compute y hat, or a prediction, and then computing our loss, and then computing the derivative, and then updating the weights. So if you were here last time, hopefully that does ring a bell, and we're definitely going to work on some exercises to help you really solidify that knowledge. But yeah, so this is the basic overview of what linear regression is trying to do. Awesome.
Yeah. So yeah, kind of to build upon that, we thought it'd be useful to go over some of the actual code and concepts that we learned last week. So what we'll be doing there is basically, if you have the, we should probably go to
the last slide.
Is that the last slide?
I think so.
There we go. Okay, yeah. So if you have your environment set up, then if you could follow these instructions and actually clone our latest repository, that would be great. So what we're basically planning to do is, while I'm presenting, essentially, we're all going to be following along and typing in the code. And then if you don't have the environment set up, then you can follow along at that link over there.
And so if you cloned the repository last time, you don't need to clone it again. You just need to do a git pull.
Yeah. Does anyone have any questions or difficulties? Yeah.
So if we already have the repository, do we just do git pull and then enter that again?
You should just be able to do git pull and then cd into week 3 classification.
Okay.
Yeah. Any other questions or issues?
So once you're done with, once you have the Jupyter notebook up and running, just kind of look up so we know how everyone's doing.
Yeah. Looks like we'll give it a couple more minutes.
If you're already ready, then you can just kind of look through some of the questions that we have, and if you already know the answers, go ahead and start typing them in. If you'd like.
Cool. Looks like most people are good. So yeah, going to the notebook now. So essentially, what we're going to do first is continue reviewing last week's workshop. So what we're going to do first is kind of go over the basics of TensorFlow, just because it is important to have a good grasp of TensorFlow, obviously, to be able to code and implement these models. So yeah, basically the first thing we want to do whenever we're writing a machine learning model or program is obviously import TensorFlow and then NumPy. If you weren't here last week, NumPy is basically a numerical computation library that lets you do computations really quickly because it's implemented with a highly efficient C backend. So yeah, that'll make life a lot easier for us. So yeah, we just imported TensorFlow. Hopefully you know it's import TensorFlow as TF, and then import NumPy as NP. And then we run that. So if you didn't know about the shortcut, it's just like Shift-Enter to run a notebook cell, or you can go to, I think it's like cell and then run cells. Or I think you can just press that. I've never done that, but yeah. Cool. So the next thing we want to do, if you remember, everything in TensorFlow kind of operates inside a session. So we can kind of divide creating a TensorFlow program into two main components. One is defining your model through the computational graph, and then two is actually quote-unquote instantiating your model by creating a session and then running your model inside that session. So just as a note, the only way you can get actual numerical values in TensorFlow is by creating the session and then telling your session to run certain operations. So we're going to create this thing called an interactive session, just so that we have a session in the background, and whenever we want to run something, we can run it easily. So yeah, if you remember from last week's workshop, that's just basically going to be, we create the name ses and call it, assign it to tf.interactive session. Then we run that. Yeah, so to kind of go over the basics of TensorFlow, we essentially want to be able to compute this function. It's basically 8 plus 2 times 3. And we want to do with TensorFlow, like obviously we can like write out the expression and have a calculator calculate it. But what we want to do is kind of define a computational graph. So does anyone know the first step to computing this with TensorFlow? Any guesses?
So just thinking back to like what we did last time, we had different objects with TensorFlow, right? We had our variables, we had our placeholders, we had our constants. So what do you think we should use in this case if we want to create this expression?
It's just tf.constant.
Exactly. Yeah.
With the number.
Yeah. So like you said, we kind of want to create constants for all three of the numbers there. So we can just do something like a equals tf.constant, and then pass in a, and then b equals tf.constant, and then pass in 2, c equals tf dot, and pass in 3. Cool. So now that we have, yeah, sorry.
Could you zoom in on this screen a bit?
Oh, sure. It's like, man. Is that better? Great. That's a little too much. I like this. Yeah. Cool. So the next thing we want to do is kind of create the graph. So right now we have our 3 numbers, and then we notice 2 and 3 are being multiplied, and then 8 is being added to the product of that. So does anyone remember how to model that with TensorFlow?
Just do the math operations on the variable.
Yeah, exactly. So yeah, if you want to be verbose about it, you can do something like d equals tf dot multiply, and then you can pass in a and b. And for the most part, when we're actually multiplying, we don't want to like write out tf dot multiply each time. So this is actually just a times b, because TensorFlow has basically said when these two things are TensorFlow objects, then overload this multiplication symbol to mean like tf dot multiply. So that's what kind of happens in the background for the shortcut. Oops, I ran that go I was supposed to. And then we have this product, and then we want to add 8 onto it. So that's just going to be really similar to a tf.multiply. It'll just be a tf.add in this case. And we want to add C and D, because D is a product of A and B. So we can assign E to tf.add C and D. And similarly, that's just going to be C plus D. So we're usually going to be using that shortcut, but just to be super verbose about it, we're going to be doing it this way for now. And now you can kind of see the idea of the computational graph. So you can just think of 2 and 3 as separate nodes, and then they're linked together with a multiplication operation. And then the result of that could be another node, and that node and 8 are linked together with an addition operation. So that's kind of how TensorFlow would model this in the background. And now we want to actually compute this and print the output. So if we think back, how do we actually compute something with TensorFlow? So essentially, yeah.
You have to run the session.
Right.
Pass in everything that you want.
Yeah, exactly right. So yeah, what we're gonna do is we have our session there created. So we did ses equals tf.interactive session. So we can just run the session and print the result of that. So if we want, we can assign it to some variables like f equals ses.run, and we want to run e, because e is going to be the sum of C and D, and D is going to be the product of A and B. So that's going to give us our entire expression, and then we can just print that out. So yeah. Passing the wrong variables. Classic. Yeah, that could be.
Anyone have any questions on what we just did there?
Cool. So moving on, as Adit discussed, this idea of a weight matrix or a weight vector is really important in machine learning. It's kind of what defines our model. When we're talking about gradient descent, when we're actually running gradient descent over and over, we're going to be updating our weight matrix, and gradually our matrix will have better and better parameter values, which lead to a lower loss, which kind of indicates that our model is doing better. So how exactly would we initialize this weight matrix? So if you kind of think back to the idea of, like, there's tf.constant, there's tf.placeholder, and there's tf.variable. So it's kind of important to know the differences between those. So in this case, we'd actually want to use a tf.variable and initialize it to some initial value. And then what tf.variable tells TensorFlow is that we're actually going to be able to update this value as we're executing our function in the computational graph. So that would be something like, we'll call our weight matrix W, and it'll be tf.variable. And then we want to initialize it with a constant. And it says that, okay, we want a constant of 0.01. So we're going to pass in tf.constant 0.01. And then we want it to be of size 10 by 1. So we can actually pass in an argument called shape, which kind of defines the dimensionality of our variables in TensorFlow. And we can just pass in the list 10, 1. So to kind of break this apart a little more, we could have actually taken this tf.constant and like basically taken it out. So we can call something like initial, and then we can just pass in initial into this. So this is exactly the same, and it kind of like is similar to what we're doing there, just like creating a constant, and then here we're basically doing the same thing, creating a constant and then initializing a trainable variable with that constant. Next, so we told so those last 2 lines is basically we told TensorFlow what to initialize our variable with, but the actual initialization of variables is only done once we tell TensorFlow, like, okay, now look at all of the variables you know about and actually initialize them. which kind of indicates that we're about to start a training session and update our variables. So the reasoning for having to manually make a call to initializing our variables is because when you have really, really complicated models, you can have up to like a million different variables, and TensorFlow doesn't actually want to take the time to initialize them until it absolutely has to. So essentially there's this object in TensorFlow called the global variables initializer, and that's what we're going to be using. So we can just do something like init is equal to tf.global variables initializer. So we basically created this init name that's assigned to this TensorFlow global variables initializer object. And then to actually initialize our variables, as we know, we kind of have to do everything within a session in TensorFlow. So we're going to tell the session to run the initialization operation, just like that. So now we should have our weight variable w be initialized. So just to make sure that everything went as expected, how can we print the values of w? Any guesses? That's a good idea, but actually TensorFlow can, Python supports like printing an entire like list at once, so you don't need to loop over it. Yeah.
Just running this session.
Yeah, exactly. So you can run in a session, assign the output to a variable, and print that output, or as kind of a shortcut, you can just do print ses.run w, and that'll run in the session, get the value, and then print it out. So yeah, it's kind of what we expect. 10. It's a 10 by 1, and all the values are 0.01. Next important thing is this idea of placeholders. So all we've done so far is we've been able to define constants and we've been able to define variables. But for each of them, we immediately specify to TensorFlow what it should be. But if you're kind of thinking about like math and functions in general, you don't normally like know that, okay, this function is only going to receive this one set of arguments. You know, you want to be able to pass in anything into a function or a model, obviously. So that's where the idea of placeholders comes in. And basically what a placeholder is in TensorFlow is it's a promise that you'll pass in an actual numerical value into this variable later. So how we're going to create placeholders is just with the standard tf.placeholder. So what we want to do is basically create, use placeholders to create an operation that gives a sum of the values passed into the placeholder. So basically what we want to do is just create like a function that adds two numbers kind of. But just to illustrate the concept of placeholders, what we can do is assign some variable to tf.placeholder, and then pass in tf.float32, which basically indicates that, okay, this A is going to be passed in a value that is of type float32. Float32 is basically like a double precision number, so like containing decimals. And then we wanted to take the sum of two values, so we can create another name. B equals tf.placeholder, and the same thing. And then we want to create an addition operation. So it's really similar to what we did up here, just with the tf.add, but we can just use a shortcut. So we just know that we have something called adder is a plus b. So now if you think of our computational graph, we have a node adder, and it basically is created from the sum of a plus b. So if we want to run the operation adder in a session and pass in two values, I guess 4 and 5 in this case, how do we do that?
You would make like a dictionary or something? Is that right?
Yeah, exactly. So yeah, if you remember this idea of a dictionary, basically, if we just do what we've been doing before, like c equals ses.run adder, this actually isn't going to work. And we get this nasty traceback, but basically the most important thing is you see this invalid argument error, and if you actually scroll all the way down, it'll say that we have to feed a value for a placeholder. For basically, we didn't pass in values for A and B. So how that's done in TensorFlow is that you pass in a second argument to ses.run, and that second argument's name is feedDict. Basically, it's a dictionary of values that you're feeding into it. And you kind of specify what do you want to feed in. So in this case, I think it said feed in 4 and 5. So we just basically say, okay, A should get 4, and then B should get 5. If you're not familiar with this object, it's basically a dictionary in Python. So what TensorFlow's, basically what a dictionary does is it associates these keys, so A and B, with the values 4 and 5. So when TensorFlow actually goes and tries to execute this adder operation, it's gonna not know what A and B are. And it's gonna go into this dictionary and look up what A and B are, and it'll find that A is 4 and B is 5, and then it'll plug in those values and do this computation. So now it should work. But also you need to print it, so yeah. Cool.
How are you running your code?
Oh, yeah, so a shortcut to run a cell is Shift-Enter. I've never actually used anything else, but I think this play also does it. Yeah, it does. So that's kind of it for our super brief TensorFlow overview. We're definitely going to be writing some actual machine learning code later on using TensorFlow. But does anyone have any high-level questions or basically like any difficulties or anything as of now? Yeah.
Yeah, when I read the first block of code, it says it doesn't understand what TensorFlow is.
It doesn't understand what TensorFlow is.
Let me get the exact error message. It says module not found error, no module named TensorFlow.
Yeah, I guess that's an issue with TensorFlow not being installed, so I guess Henry will help you with that. But yeah. What's up?
I have TensorFlow installed, but then whenever I try to run a shape, it says
Oh, I remember.
I had TensorFlow installed at some point, but wait, did I delete TensorFlow?
So which line of code?
No, yeah, that. It's like some bug with TensorFlow. It's this thing. It's like it doesn't know what the shape is. What? That is some issue. We saw it last time. No, it literally doesn't know what shape is. So it's like this. I remember like someone had this last time. Yeah, I remember. So yeah, we've actually seen that before. It's like an issue on TensorFlow's end. We don't know exactly what causes it, but he's looking it up, and then he'll be there to help you out. What's up?
Is it Matplotlib?
No, it's a TensorFlow. Like it basically, I think it was in this line of code, right? This shape. I think that's where like shape. It said shape wasn't defined. But yeah. Yeah, so kind of we've used a little bit of NumPy and TensorFlow, and kind of the other library that you'll be using a lot in machine learning is this library called Matplotlib. Essentially, it's a super useful library that lets you visualize data. So there's a lot of reasons that you might want to visualize data. Just kind of, you can see how your features relate to each other and how your features relate to the output. So if you were here last week, when we looked at the housing data set, we kind of plotted things like crime rate or quality of schools against housing prices, and we were able to observe that while there was some sort of relationship, the relationship wasn't really strong, so we knew that we had to use a lot of different features in our regression. But sometimes when you're actually using Matplotlib to visualize your features, you'll see that, okay, these two features are exactly correlated, so actually one of them is redundant, and I don't even need to spend the computational time looking at that feature. So that's why we think that basically using Matplotlib to visualize your data set is a good idea. And essentially, kind of some demos with Matplotlib is basically the most useful thing is obviously plotting functions. So what we've done here is we've imported matplotlibs. I should get my charger. 1 second. Okay, yeah, sorry about that. So basically, we import matplotlib's object called pyplot, which is basically the object that you use to plot things, and then we just named it PLT just for shorthand. And then we created this object x, and we assigned it to np.linspace 0, 10, 100. And all this does is it returns 100 evenly spaced numbers, or sorry, that should be a 10. Returns 10 evenly spaced numbers between 0 and 100. So this 10 kind of so basically you have 0, 100, and 10. And we take cosines, we basically compute the sine and cosine of both of that, and then plot that. So it's gonna look like this. Oh, sorry, this should be 100 evenly spaced numbers between 0 and 10. Yeah, but basically, yeah, we can use matplotlib to kind of plot functions. And another thing that's pretty cool is bar plots in matplotlib. So say you have these 3 objects like eat, sleep, and code, and then you spend, say, 1 hour eating, 0 hours sleeping, and 10 hours coding. So you can kind of create a bar graph by calling plt.bar. And basically this range len performance kind of specifies that we'll have len performance objects, so that's 3, and we want to plot the performance. And on the x-axis, it'll specify that the names of the bars are eat, sleep, and code, and then we just give a title to it and show it. So yeah, it'll look something like this. Yeah. Kind of the last thing that we want to be familiar with in matplotlib is we can actually use matplotlib to visualize images, which is pretty cool. Because at the end of the day, all an image is it's just a matrix of pixel values between 0 and 255. So there's no reason that matplotlib should be able to plot those also. So kind of what we do is I just imported this digits dataset from scikit-learn, and then so we can run that, and that might take a while, but we basically take so we take the first 5 images, and then for each of the images, we basically plot it. And when you're plotting an image, the call you make is plt.imshow. And since it's a grayscale image, you have to pass in this argument, plt.cm.gray, since the digits are in grayscale. And yeah, don't worry about like memorizing any of this. You can just kind of Google it when you get an error. So yeah, the imshow command kind of shows an image, and then you call plt.show to show all of the plots. So when we run that, we kind of get these images. And they're not very well defined just because this data set is really small, and each of the images are like 8 by 8, so yeah. Does anyone have any questions on matplotlib, TensorFlow, NumPy so far?
Is there any other data sets of images?
Yeah, so we'll actually be looking at different image data sets kind of later on. So there's this other data set called ImageNet, which is basically a compilation of like 1,000 different images. And that's kind of used as a benchmark for training convolutional neural networks, which is like an advanced type of neural network that we'll be looking at later. But yeah, there's definitely a lot of different types of image data sets. There's also like data sets of medical images for people who are interested in using machine learning to identify diseases and stuff like that. So yeah. Cool. Yeah, so the next thing we'll be doing is, I'll go through this pretty quickly just because Adit has gone through a lot of the machine learning basics. But just to rehash some of his ideas, the main point is we have a bunch of training samples and they're pairs of features and outputs. So yeah, we've called it a lot of different things. You can call like X, like just X, or features or inputs, and Y we generally call the outputs or the label. And for example, you can like do machine learning on all sorts of different data. So as we looked at, as the data set we looked at last week, it was, we had a bunch of features corresponding to a house. So we had like crime rate, quality of schools, lot size, number of bedrooms. And then the output of that was the value of the house. And we sought to learn a model that basically used linear regression to predict the price of a house. And one thing to note is we can't exactly use anything we want as data. So obviously, like if you're using words or images in their raw form, like we humans can interpret, computers won't really be able to make great use of that data, just because like everything most computers obviously interpret as numbers. So what you can do there is, like, say you have a feature that corresponds to the neighborhoods a house is in. So if you think back to the PowerPoint when Adit was presenting, we kind of mapped like 0 to one certain neighborhood and then 1 to another neighborhood. And basically that's how we deal with variables that aren't necessarily like numbers already. We kind of just map them to numbers. And it's important to do that in a consistent way, just so you can go back and forth for when you're training a model and when you're actually writing your outputs. So yeah. And then kind of the most important thing to note about machine learning in general is it's all about generalizing from the training data that we have, which is why machine learning is like difficult in the first place. If all we wanted to do was learn one function that gets like 100% accuracy on the training data, that's really easy because we could just like make a lookup table. But obviously that wouldn't be useful in practice, because in practice we're actually going to get inputs that we've never seen before. So we want our model to work well on that, and that's kind of where this idea of machine learning comes in. Another important thing to note is this idea of loss functions, which Adit also touched on. So we have this function f that maps inputs to outputs, and then we want to see how well it's doing. So obviously if it's really bad, we want to know like, okay, it's really bad, and that's going to be indicated with the high loss. So for example, say we have real valued outputs like we did in the case of linear regression. So maybe this f of xi is like $20,000, but yi, which is the actual house price, was $50,000. Then we're going to have a pretty big loss just for this single pair. And then if you look back here, we have several examples of training data. So we can kind of evaluate the loss on each one. So we evaluate this li for I going from 1 through n, so basically through all of the data points, and we sum that up, and that gives us our total loss. And what we kind of do in machine learning is when we're trying to learn these parameters, we basically seek to minimize this loss. And kind of the assumption that we make is if we minimize this loss, then we've learned a good function that can accurately predict, that should be outputs from inputs, but yeah. So basically this idea of minimizing the loss on the training data set, so yeah, do people think that's actually a good idea? And what are some arguments basically for and against that? So if you think back to the idea of generalization, basically, why might just minimizing this loss not be a great idea? Yeah. Exactly, yeah. So essentially, you mentioned overfitting, and overfitting is basically a phenomenon when the parameters you learn in your function basically correspond too well to the data set that you trained it on, that they actually start to fit to the noise in the original data set, rather than learn a general function that works on data it's never seen before. So how that can happen is, say there's some setting of parameters that brings this loss to 0. That doesn't necessarily mean your model that you've learned is a good one. It can mean that just for this particular data set, our learning algorithm was able to find the exact setting of parameters that minimize this loss, but maybe the setting of parameters was way off for other data it's never seen before. And that's kind of why machine learning is tough. You never really know how much your model is overfitted. Obviously, there are some like really clear signs when you have like 100% accuracy on your training data and like 20% accuracy on testing data. But other than that, there's a lot of active research going on how to minimize the risk of overfitting, and we will be going into some of the basics of that a little bit later. But yeah. And we've kind of already gone over the idea of linear regression. Essentially, this function f, to kind of make it concrete, we just have it as a vector-vector multiplication. So say you have n features. For example, the features that describe a house, you'll have a weight for each of those. And then your output, basically your prediction for the price, is going to be given by taking a dot product, basically. So for each weight, for each feature, you take the weight that's assigned to it, multiply, do that for all the features, and then take the sum. So yeah, it's basically the overall kind of view of linear regression. But yeah, the idea is we're going to initially randomly initialize these weights, and we're going to have a really high loss. And then, as Adi kind of discussed, we're going to use gradient descent to minimize that loss and hopefully learn a better setting of parameters. So now we're actually going to go back to our slides and kind of discuss classification, which follows pretty intuitively from the ideas behind regression.
Okay, cool. All right, so just before we start with classification, I just had a quick kind of question for everybody. So what do you notice about the outputs of a linear regression model? So there's something in particular about these outputs. So just kind of think about that. And then what are some other cases you can see linear regression being used for? So in the example we talked about before, we talked about house prices, right? We talked about how if you're given data about houses, like information about their bedrooms, square footage, etc., we can then predict the house price. So I want you to just talk to the neighbor next to you. If you don't know them, introduce yourself. But yeah, just kind of talk about these questions.
So what do you think?
Can you think of other things that other outputs have come up? Yeah, that's kind of what I was doing. It's like the difference between linear regression outputs and real linear regression. So yeah, so really classification is
Yeah, I guess we need to take something out of the weight matrix. Maybe.
So did anybody come up with any ideas for the outputs of the regression model?
Grades based off of the number of hours.
Definitely, yeah. Essentially, yeah, like a lot of different things, kind of like any time you want to model something, when you're regression, it's like what year? Nice. Oh, nice. PhD or master's? Nice. In what?
Applied economics.
Oh, wow, awesome. Nice. Oh, you are? Oh, nice.
And then you get
Oh, nice. Yeah, we have I thought like most people see it. Not like
any type of data set.
Alright, cool. Thank you guys for discussing. So what were some of the responses that you guys talked about? What were some of the use cases or with the first question, what did you notice about the outputs?
Numeric.
Yeah, numeric. That's good. Good response. Anybody else? Anybody else with use cases? Some other things you can say? Or the first question? Yeah. Cool. So with the first question, what we really wanted to hit on was the idea that the outputs of a linear regression model are real valued numbers, right? So if you think about the house price prediction, you always know that the output is going to be some scalar value, right? So that was something that we wanted to hit on. And you'll see the difference between what the outputs of a linear regression model are between the outputs of between a classification model instead, right? So any other use cases that you can see linear regression being used for? The idea that we do have outputs that are scalar valued numbers. Anybody have any thoughts on what those use cases might be?
Whenever you have like a set of input values that give you a set of output values that just plot it out, then you can.
Yeah. So for every input, you have a specific output, and then you can then visualize that in like a graph format or using matplotlib. Yeah, definitely. Okay, cool. So that leads into classification, right? So like we talked about, the outputs of linear regression models are real valued numbers. And so, on the other hand, we have machine learning models that fit more under the classification category, which means that the models in this category seek to identify a particular class or a category that an example belongs to, right? So the outputs of a classification models are likely to be either single numbers or more likely probabilities that represent each class or category. So we'll see what this means with an example. So like we talked about before, right? We have predicting house prices. That's a problem that we can solve with linear regression because we want a scalar output as the result of our model, right? We want to take in the information about the houses and we want to predict a price, an actual price for it. On the other hand, you can think about another task such as identifying a digit from a handwritten number, right? Let's say we took a picture of a handwritten number 9 and we want to determine what digit that is. And so if you think about this, the output of our machine learning model isn't necessarily sometimes what we want to be a number. We want it to be more of a probability among different classes, right? We don't want our classification model to output, something negative or something outside of the range from 0 to 9, right? We just want this to be a 1-digit classifier, and thus we have these 10 different classes that represent the outputs that we can have, right? So in this particular case, we have 10 different digits that we want to choose from, and so the output of our classification model will be a set of 10 probabilities that represent how likely it is for that particular class to be outputted. All right, so logistic regression is a machine learning model that fits under this classification category, and so it's used for problem spaces where a selection from a group of categories is needed. And so if you think of example problem spaces, you can think of something like cancer detection, something like taking in a medical image and then being able to determine yes or no, is this representative of a patient who might have cancer or not. So that's definitely a binary classification task. And so binary basically means that there's only 2 options, right? It's either a 0 or a 1. And then you also have digit classification where you have 10 different classes that we can choose from. And then we also have something like object classification where we want to determine if the image represents a dog, a cat, a horse, a bunch of other classes like that. So that's something called a multi-class classification. All right, so the function for logistic regression is very similar to that of linear regression. So as you remember, with linear regression, the outputs are a linear function of the inputs, and then you add a bias term. So it's going to be x times w plus b. And then, so with the logistic regression equation, we're going to have that same linear combination. We're going to have x times w plus b. But we're going to add we're going to pass that through a function. And so this function, we can think of as 2 different ones. So this depends on the type of classification task you have. So for binary classification, so for when you have 2 different classes you want to choose from, this will be the sigmoid function. And then for multi-class classification, this will be a softmax function. So the sigmoid function. Sorry, go for it.
No, that was it.
Yeah. So we'll go into that. So the sigmoid function, as you can see, is so you may have come across this sometime in your mathematical careers, but it's basically the function 1 over 1 plus e to the negative z, and so the softmax function is this thing that does. So I think the best way to explain softmax is just through an example. So let's say for our vector x, right? Let's say our vector x is 5, 1, and -2, right? So that's going to be our x. And so the x sub j just simply represents each index within the vector. So you can think of x sub 0 as 5, x sub 1 as 1, and etc., right? So that's just a notation that we're going to use. And so when you pass the vector x through this softmax function, what it's going to do is that it's going to look at each of the values. So let's say for 5, right, we're going to do e to the 5 over a summation of all of the other values in x, or all of the values in x, exponentiated. So we're going to have e to the 5 plus e to the 1 plus e to the -2, right? So this is going to be our first value in the output of softmax of x. And then we're going to do the same thing for the second value. So we're going to do e to the 1 over this same summation. So e to the 5 plus e to the 1 plus e to the -2. And then we're going to do e to the -2 over that same summation. Right? So that's basically what a softmax function does. And so going off of that, think about what adding this sigmoid or softmax function does to the output. Right? So if you remember our linear regression model, we just had x times w plus v. But here with logistic regression, we're passing this through another function, either a sigmoid or the softmax. And so just talk about this with the person next to you. Think about what the effect of adding that function does. And so, yeah, just try out seeing what sigma of xw plus v is, and then see if you can notice something unique about that. I like to write it down if that's helpful as well.
Oh, very nice.
Alright, cool. So can anyone tell me what types of things they talked about? Did anyone notice something unique about what results from the softmax, from passing something through the softmax function?
It gives you a value between 0 and 1.
Yeah, perfect. And then there's also one other thing. So all the values are between 0 and 1. And anybody else?
Positive?
Yeah, positive, yeah. Yeah, because it's exponentiated, yeah. Anything else?
I think it's saying like, given all the other predictions or different cases, like how confident it is.
Yeah, you can definitely interpret these as probabilities, Right. Yeah. So the last thing is that all of these values will add up to 1. Right. So if we had that particular case with x, so I don't know the exact values of those, but you can definitely safely assume that the one on the value on the left will be the largest with respect to the other values. So you can think of these as relative probabilities as well. So I guess the value on the left would probably be somewhere around 0.8 or 0.9, and then definitely the value on the right would be something that's 0.01 or 2. Cool. Okay, so with linear regression, we talked about loss functions, right? Loss functions are something that's very general to any type of machine learning model. Yeah, go
I'm
for it.
sorry, what did we say about the other one, the sigmoid?
Yeah, so.
Oh, okay, yeah. So basically, sigmoid, you can think of the sigmoid function basically operating on a single input. So like sigmoid of 5, that will give you some value between 0 and 1, and you can kind of interpret that as a probability. So say because essentially if you think back to linear regression, we had real valued outputs, right? So we want to squash that into something between 0 and 1, and the intuition is like, think of it as a probability. If we squash it and we get like 0.96, then the binary label that corresponds to is probably 1. If we get something like 0.01, then the binary label that probably corresponds to is 0. If we get something like 0.4, 0.5, 0.6, then we're not really too confident. So that indicates that on that particular example, our model probably didn't do too well. So that's the idea of sigmoid. Basically taking a real valued output and squashing it into something between 0 and 1 so that it can be interpreted as a probability, which is useful for binary classification. And then with machine learning and classification, we don't always want to do binary classification, right? Because if we had like Adit said, like the MNIST data set, there's 10 different classes, so we won't really succeed if we're trying to do binary classification there. So we actually want to do classification across 10 classes. So you can think of softmax as a generalization of sigmoid in that it operates on a vector. So the actual equation that Adit wrote down is like for a single number, but think of it as being applied like for each number in the vector, and it's gonna return a list, right? Because you passed in a list, and then each element in that list, the sum across all that will be 1, and the probabilities will be like weighted relative to each other. So like Adit said, like this one probably will be like 0.8, this one might be like 0.15, that'll be like 0.05. So it kind of gives you like relative confidence against each other.
Thanks, that makes sense.
Yeah, so with linear regression and with all machine learning models, we have some sort of loss, right? We want to determine how off or wrong our prediction was compared to the actual training label. And so with linear regression, we use something called the mean squared error loss. And so with logistic regression, we're going to use something else. We're going to use this thing called a cross entropy loss. And so we're going to delve more into this when we are actually coding it out, because that's something where we can use a TensorFlow function for. But just to make you guys aware of this, there are different loss functions, and that the cost entropy loss is just another measure of measuring the difference between the prediction and the actual values. Okay. And so just to kind of give you guys a bit of a view of what the cost entropy loss is doing, is that you can think of it as just being, like I said, a measure of how, I guess, wrong our predicted value is compared to the targets, right? So if you think about, let's say if we compute a y-hat that has the following values, and we have an actual target, or a target label that has 0, 0, and 1, you can think of just intuitively, right? We want our y-hat we want this value to be higher, and we want these values to be lower, right? So we can compute this cross entropy loss, where we basically want to determine how far our computed value was from the targets, right? So you can take a look at how this expands out, and that will give you a number that that represents how wrong your prediction was.
So to kind of build off of that, so first of all, like that negative natural log 0.4 is going to be a positive number, because if you take the natural log of something between 0 and 1, you'll get a negative, and there's a negative out there. So it'll be a positive number, and that kind of quantifies how off your model is. And then as Adit mentioned, since there's a 1 in kind of the second index of targets, basically like we're thinking like, okay, our label is 2. If you're thinking of like, say, digit classification, the first index corresponds to 0. Sorry, the 0th index corresponds to 0, first one to 1, second one to 2. So in this case, like say our target is 2, and we computed basically that we think there's a 0.3 chance of it being 0 or 1, and then a 0.4 chance of it being 2. So that's why we get that loss. And as we train our model, hopefully our predictions get a lot more confident. And say that 0.4 actually approaches 1, then we know that the natural log of 1 is 0. So we'll actually have 0 loss, which makes sense because nothing's wrong there. And then say our prediction was even worse than 0.4. So say that 0.4 approaches 0. So as argument into natural log approaches 0, the value approaches infinity. So like natural log, a really, really small number, is going to be like negative. It's going to be close to negative infinity. So we're going to have obviously a really big loss. So that's kind of how you could think of the loss as modeling how off we are in our classification.
Any questions on it? Awesome. Okay, so now that we've talked about the equation for logistic regression, let's think about a problem space that we can apply logistic regression to. This is a very classic problem in machine learning, the idea of being able to take handwritten digits and predict the most likely digit for every test image, right? So we have a data set of both images and labels for each of the numbers. And so we want to be able to create a machine learning model that predicts what digit that image represents. And something that is important to note is that labels for each of these images, when we're thinking of classification and when we're thinking of inputs that are related to particular classes or categories, we want to label them as one-hot vectors. So instead of having this, having the label for the number on the left as being 5, we want to create an n-dimensional vector where n is the number of classes that you have. So in this case, we have 10 different classes. We want to choose between the digits 0 through 9. So we have 10 different classes, and we want to have a 0 for all the classes that don't represent the object, and then a 1 for the class that it does represent, right? So if we're going by zeroth indexing, this will be the 5th position will be a 5, and then same with here. Okay, so then we can also think about the inputs and outputs to our machine learning model. So the images for MNIST are 28 by 28, and so those can be reshaped into a 1 by 784 sized vector. And so the outputs are going to be a set of probabilities, 1 for each digit between 0 and 9. Right? So you can see that we have a 1 by 784 size vector, where each of those values is going to be a number between 0 and 255. So basically 255 meaning it's completely black, and 0 meaning it's white, or the other way around. But basically you have pixels 1 through 784 in that vector. And what we want to do is we want to create probabilities for each of the different classes. Okay, last couple questions. So now that you know what the inputs and outputs are, think about what the shapes of the outputs, of the inputs, of the weight matrices, and of the bias term. So with machine learning, determining or identifying the dimensionality of all the components that you're working with is going to be very important. So just think about what the shapes of the inputs and outputs, or the sizes of those values are. Just talk about it with your neighbor just for a minute or two.
Sorry, this is like the number of examples, and then it's like the column, like the other that's like if you take object sizes, it's like the location of the space like population.
Oh, is it on the?
I guess for one image. So if there's like a bunch of images, and it's just one case. I guess how many every number.
Alright, cool. Thank you guys. So, does anybody have any thoughts on the answers to these questions? On what you think the sizes or the shapes of these, of either the inputs, outputs, or weight matrices or bias terms are?
The bias term should be one by one. Because it's like just a constant thing.
Yeah, so the bias term is actually, so let me just give you the answers. That's actually going to be a 1 by 10 term. So let's examine why these numbers are. So with the inputs, right? I kind of just gave you that on the slide previously. We have a 1 by 784 size vector, and so that comes from taking our 28 by 28 images and just concatenating all of those into, or just expanding it out into one large vector. And so when we're multiplying, if you think back to the equation, right, we're multiplying x times w, and what we want is a set of probabilities, right? So we want, if you think about matrix multiplication, right, when we're multiplying two matrices, we want these inner terms to match up, and then the outer terms will be the size of your output, right? So what we wanted was a set of probabilities for each different class, and we had 10 different classes, right? So when we multiply these two terms together, we're gonna get an output of 1 by 10, which is shown there. And so going back to the bias term, so 1 by 1 is a good answer, but let's think more about what we're doing here. So the output of this computation will be 1 by 10, right? And so when we have an addition between two vectors, we definitely want them to be the same dimensionality. And so what you're thinking of might also be right if you want the bias term to maybe be the same across all of those 10 values. So that could be something that could work out, but generally we want that bias term to be the same dimensionality. Do you have anything?
Yeah, basically what I was going to say.
Okay, cool.
So we're gonna have 784 different probabilities, right? After that.
So we're gonna have 10 probabilities. So just going back to x times w. So x is 1 by 784, and then w is 784 by 10. So when we multiply those two, this is gonna create a 1 by 10 vector or a matrix.
Right.
And then add that to a 1 by 10, you still have a 1 by 10.
Yeah, I get that, but in the input/outputs page, it goes from pixels 1 to 784.
Yeah. So the inputs are 1 through 784. So 1 by 784 matrix. But the outputs are going to be a set of probabilities, right, for each of our classes, and we have 10 different.
Yeah, what are the 10 classes? Maybe that's.
So it's we basically our problem space is that we want to take each handwritten digit or a handwritten number and determine what digit it is. So we want it to be something from 0 to 9.
Okay, thank you.
What exactly is a bias?
Bias. So it's similar to a weight matrix.
Basically, kind of high level idea
Yeah.
to think about it is think back to linear regression, right? The equation for that was y hat equals x times w plus b. So think about what would happen if you didn't have that b there, and kind of just like the two-dimensional case. That would mean that the model always has to go through the origin, right? And it's not, for the most part, our data isn't going to be like of the case that it's linearly spread about the origin. It's going to be shifted up or down. So in a two-dimensional case, that bias term hopefully you can visualize like it shifts the decision boundary up and down. And then when you have more dimensions, it's not called a line anymore. It's called like a hyperplane. But all that bias term serves to do is shift that hyperplane.
Good question. Okay, yeah, so with the process of training this logistic regression model, it's generally the same process as what we had for linear regression. We're going to take each training example and pass it through our function and compute a prediction for y hat. So this is going to be a set of probabilities. As you can tell at the beginning of training, these probabilities are all going to be probably uniform. So it's definitely not going to know whether something is more likely to be a 1 or a 9 or a 6 or whatever. But basically after that, we would measure our loss. We would compute our loss by comparing y and y hat by using the cross entropy loss. And then we're going to compute our DL, DW, or our derivative with respect to the weights, sorry. And then we're going to update our weights and repeat for a set number of iterations. And so we'll definitely go into more of this when we're looking at coding up the model with TensorFlow. Yeah, so let's do it.
Yeah, awesome. Yeah, so back to coding, I guess. So yeah, high level, Adi kind of went over a lot of this, so I'm not really gonna go over it again. But just as a reminder, the sigmoid function kind of takes a real valued output, which is what we get in linear regression, and squashes it between 0 and 1. And then we can interpret our outputs as probabilities, and then map that to 0 or 1 based on whichever one's closer, basically. And that's kind of how we can immediately go from a regression framework to a classification framework. So yeah, so far that kind of lets us do binary classification, which is pretty useful. Like it can be obviously used for a lot of different cases. Like if you're trying to produce, like say the risk, if you're trying to predict, say the risk of a patient having cancer, given a bunch of health data about previous patients, then you want to say like you know, a certain probability, this patient has cancer with a certain probability. So binary classification is really useful. And then another useful type of classification is multi-class classification, which is something that is a generalization of binary classification. So with this, an example is, say you have the MNIST digits, the digits are between 0 and 9, and so we have 10 different classes. There's also like other data sets such as ImageNet, which actually have 1,000 different classes. So this idea of multi-class classification kind of generalizes to any number of classes. But yeah, so if we consider our MNIST problem, we essentially want to predict one label out of a possible 10. And one way, if we only know binary classification, that we can do this, is that we can just train these things called one versus all classifiers. So we can make one classifier that basically says, this is a 0 or not a 0. And then we can take another classifier that says, this is a 1 or not a 1. And we can have 10 of those classifiers. And we can basically take a prediction, run it through 10 different classifiers, and take the output which it's most confident about. So kind of the downside of that is obviously we have to train 10 different classifiers, which is no good. And then at prediction time, doing a prediction is a lot more expensive, and you have to take care to make sure that actually predicting something from an input is not expensive, because if you actually deploy this machine learning model, people want their predictions quickly, obviously. So we can actually do this all with one classifier, and how that's going to be done is through multi-class classification. So yeah, we kind of have this equation that Adit already gave. He kind of gave it in x times w plus v, but this is essentially the same thing. The shapes line up, and kind of how you can think about it is, say you have some image. So yes, that's a cat. Then you basically take the pixels and stretch it into one vector. And then you take a weight matrix and multiply the pixels with that. So essentially how this matrix multiplication will work is, for the very top one, you'll take 56, multiply with 0.2, 231, multiply with negative 0.5, do that for the rest, and then take the sum. So that's just a vector-vector multiplication. So that'll be a single scalar value. Then you'll do it for the second row, you get a single scalar value. Then you do it for the third row, you get a single scalar value. And then you add the bias term. And it essentially, you take the sum, and it gives you a score. So essentially, currently, based on the setting of those parameters, these are the scores it got. And then you can run this through the softmax function, which will essentially take these scores and convert them into values between 0 and 1 that can be interpreted as a probability. So if you imagine what the softmax scores could be, This is the largest, so it'll probably have a really high score, and this will have a really small score. So you can probably realize that those settings of weight parameters are probably not ideal because that is the cat. So yeah. And kind of to go over the cross entropy loss a little more, which Adit touched on, but essentially how it's computed is you have your one-hot encoded labels, and then you have your probabilities, and you can kind of see that in this case, we did not predict the correct label with high probability, so we assigned the wrong label a probability of 0.7, the correct one a probability of 0.2. So we have the loss across this one training example being 0.7. And then when you invert those two, so we assigned to the correct label with the higher probability, our loss went down. So that's kind of the intuition behind the cross entropy loss function. And then essentially what this equation is doing here is that we are taking our cross entropy loss, so that's C of S and L, where L is the actual label. So in this case, it would be this one hot encoded label. And then S is what we predicted. And our prediction was given by, as Adit mentioned, running the product WX plus B through a softmax. And then we're basically taking that, and then we're evaluating that for each data point and taking the sum and then taking the average. So that'll be kind of our loss function across the entire data set, which is what we're going to implement. And then, yeah, we're just going to do gradient descent and learn the optimal parameter values. Yeah.
Is the equation W times X, or is it X times W?
It really depends on how you have your shapes line up. So if it was X times W, where X was, say, 1 by 784, then W would be 784 by 10. And then I believe I wrote it sort of differently. I wrote it like W transpose X. So I guess the shapes for that, so X would be, X would be a column vector instead of a row vector.
Okay.
So yeah, essentially you use that transpose to just make sure that the shapes line up. Cool. So I guess now we can actually start coding this model. So we're just going to use our normal inputs, NumPy, TensorFlow, and we're going to import the MNIST dataset. And essentially, TensorFlow kind of comes pre-built. It comes with a bunch of datasets built in. So we can just basically load the MNIST dataset, and we can specify one hot is equal to true, which basically relates to Adit's idea about converting each label into one hot vectors, so that computing our loss works out a lot easier. So yeah, that's kind of all that is doing, so we can run that. Next, we want to define some, these things are called hyperparameters, which I'll explain in a second. But basically, we define three things. One is our learning rate. The next thing is our batch size. And then the final thing is the number of iterations we will do. So kind of what our learning rate is if you think back to the idea of gradient descent, each time we take a partial derivative of our loss function with respect to the weight variable, we actually want to update our weight with that value. And then where learning rate comes in is the learning rate is how much we scale our update by. Essentially because sometimes that update is really, really large, and doing such a large update to our weight value may actually take it in the opposite direction. So we kind of scale our update by the learning rate. Next is this thing called batch size. So the MNIST dataset has 50,000 examples. And previously we've been saying that for each iteration, just loop across all of the different examples, which is not very efficient just because there's 50,000 of them, so we'd be just like sitting here waiting for our model to run. So we can actually specify this thing called a batch size, which basically tells TensorFlow that, okay, instead of looking at all 50,000 examples, just look at, in this case, 128 of them randomly and compute the gradient that way. And finally, this number of epochs is how many iterations we're going to do. So in this case, for 2,500 iterations, we're going to randomly take 128 examples and run our optimization algorithm on all 128 of those. So back to kind of coding up our model. So the first thing we need are placeholders for x and y. So we're going to want it, when we create our model, we're going to want to pass in data into x and y. So that's why they're going to be placeholders. So if you kind of remember, that's just going to be with done with tf.placeholder. So you have x equals tf dot placeholder, and then we pass in float 32, and then we also pass in the shape. Okay, and then, so it's going to be none in 784, and that none kind of specifies to TensorFlow that I'm not exactly sure what shape I'll pass in here, but I know that the second one will be 784. So if you remember, each image is 784, and if we don't pass in an actual concrete value here, we can pass in a matrix where this is essentially anything. So that kind of is super useful because we can run a prediction with one image, so that would be a 1, or we can run a prediction with, say, 50,000 images, so that would be 50,000, and our graph won't throw any errors because it's expecting a variable shape. So yeah, and it turns out that this shape isn't actually going to be going to cause any errors in our matrix multiplications, just because when we multiply this with our weights, we'll need to make sure that this 784 dimension lines up. Yeah.
Why isn't the first parameter just the batch size?
Which one?
For instead of none.
Oh, so this is what we're, so yeah, so basically if we're confident that we're gonna be using the batch size every single time, then it can be the batch size for sure. But say like, I train with the batch size, but say I wanna do 50,000 predictions, or I just wanna do one prediction, then it'll be more useful instead of having to create kind of like a whole new graph just to change that one number, to just change it on the fly, which is what TensorFlow supports. So we kind of do the same thing for our labels. We call them Y. So it's a placeholder, pass in tf.float32, and kind of the same shape. And as we mentioned, there's going to be a vector of 10 numbers returned, where each one is going to represent the probability that that index was the digit. So cool. Does anyone have any questions so far? Or cool. So the next thing we want to do is create variables for our weights and biases, and these should be tf.variables because obviously we want to be able to train them. So we'll be using tf.variable for that. So we can call our weight w and just be like tf. And this will be the same thing for a bias. So yeah, what we kind of did here is we created that weight matrix which Ajit was talking about. It's going to be 784 by 10, so that when we run it with a matrix multiplication with x, we get some shape by 10, which basically represents that, say this none is 1, then we'll get one vector of 10 outputs, and it'll give the probabilities for that one example. If this is actually 100, then we'll get a 100 by 10 matrix, where we basically have 100 vectors. We basically have a list of 100 values, and each value is a vector of size 10, and that will give the probabilities for all 100 different images passed in. And then similarly, we initialize our biases with the shape 110, and we're basically initializing them with zeros. It's not particularly important at this point what exactly we're initializing our weights and biases with, but when we get into kind of more complicated models like neural networks, it'll turn out that initialization is going to be pretty important to be aware about. And then yeah, TensorFlow kind of makes doing our logistic regression model really simple. So all we need to do is a matrix multiplication with x and w, and then add the bias to it. So just to make sure, yeah, it looks like the shapes line up there. And then we run it through the softmax function, and I call that name normalized logits. Essentially, in the machine learning community, they call like your predictions logits. I'm still not really sure why. And then normalized logits are basically, we ran them through the softmax function, so we know that they're normalized, which means that the sum is going to, sum of all the elements in the vector is going to be 1. Cool. The next thing we want to do is write down the losses that we discussed. So as Adit said, we kind of use cross entropy when we have a classification scenario, and then we use the mean squared loss when we have a regression scenario. But really, TensorFlow won't really care what loss we're using, so why don't we just try both and see which one works better. Yeah, so the way we can implement the cross entropy loss is that TensorFlow has this function called softmax cross entropy, and all you need to do is pass in your predictions, which are these, and then pass in your actual label. And it does two things. It computes the softmax function, so it basically does this, and it also computes the cross entropy with respect to your label. So the way you can do that is tf.nn.softmax entropy with, and then we're going to pass in our labels, which are y, and then our logits, which are so yeah, what this is kind of doing is TensorFlow kind of has a module called NN, which stands for neural network. It's not particularly important right now, but it has this function called softmax cross entropy with logits, and we need to explicitly define what our labels and logits are, just because the TensorFlow developers decided that imposing a certain parameter order is worse than having the user explicitly specify what they are. So here there's no ambiguity which one our label is and which one our logits is. So yeah. And then kind of similarly, we can write down the mean squared loss. So as we kind of discussed, the mean squared loss is given by taking all of the losses across each prediction, where the loss is basically going to be the difference between our predicted value and our actual value, squaring that, and then taking the sum across everything in our data set. So the way we can do that with TensorFlow is through the TensorFlow call called reduce mean, which I'll explain in a second. But essentially we call tf.reduceMean, and then we square the difference of our predictions and actual values. So our predictions was called logits, and our actual values were labels. So yeah. Oh, and these should be the normalized logits. Oh, and this is y. Yeah. So essentially what we did here is we took these normalized logits and we basically took the difference between those predictions and our actual values, squared that, and then what reduce mean does is it passes in a list of all these differences squared, and it basically sums them up and takes the mean.
Wait, why do you have to pass in normalized logits?
Oh, yeah, good question. So basically, remember how we talked about the softmax function? It kind of takes our vector of real values and squashes them so that each one is between 0 and 1. So we can interpret them as probabilities. The reason we didn't have to do that for cross entropy is that this function actually computes the this exact value for you, but tf.reduceMean doesn't. So that's kind of why. And kind of to get a little bit nitty gritty, the reason that TensorFlow actually wants to compute the softmax for you instead of you doing it yourself is because this is actually like not numerically stable, and then there's something else that they use here that is more numerically stable. But yeah, that's pretty nitpicky. But yeah, it's something that the TensorFlow developers just kind of messed up on. Or not messed up, it was just a design decision, I guess. But yeah.
Is there any way to see function how it looks like in the documentation?
Oh, are you talking about what the actual computational graph looks like? Yeah, actually there is. So there's this part of TensorFlow that they made called TensorBoard. And what TensorBoard is basically a web UI that allows you to visualize what your computational graph looks like. Right now our computational graphs aren't very complicated, so we didn't do that. But kind of when we get into bigger neural networks and convolutional neural networks, we'll definitely be able to use TensorBoard to visualize what our graph looks like. Any other questions?
This,
Yeah.
This might not be a good time. I'm okay with asking later or before
Yeah,
next
just go
time.
for it, yeah.
But can this be ran like on PyCharm?
Yeah, so PyCharm is like an IDE, right? So yeah, I think if you instead of using Jupyter Notebooks, like if you just like take all this Python code and like paste it into PyCharm, it'll definitely run. I don't see why it wouldn't.
Thanks.
Yeah, no problem. So finally, we have this loss, and then the last thing we need to do is this idea of gradient descent, which luckily we don't need to implement the actual taking the derivatives ourselves. We just need to create a gradient descent optimizer object that TensorFlow has and tell it to minimize our loss. So then we'll have that operation, and all that operation basically does is when TensorFlow runs that operation, it's going to take in all of the data and then do one iteration of that operation and then modify our weights once. So we're going to basically run this a bunch of times. So what that's going to look like is to create this optimizer, we'll call it opt, and it's going to be tf.train.gradient descent optimizer. And we're going to pass in our learning rate, which I called LR. LR. And then we're going to tell it to minimize our loss. So this is our loss, which for now I put as mean squared loss. And then we'll create an optimizer, basically gradient descent, and tell it to minimize our loss with a certain learning rate. Cool. And then these two operations kind of will help us keep track of how our accuracy is. This basically tells us that given a set of predictions and a set of actual labels, basically get the correct predictions. So that's what CP stands for. And then basically it's going to return a 1 if the prediction is correct and a 0 if the prediction is wrong. So from there we can just take the sum and then take the mean to see our percentage accuracy. So that's what that tf.reduce mean is doing. And that cas is just, because I think these are like Boolean values, it converts them to 0.0 or 1.0, whether based on if it was false or true. Any questions?
In gradient descent optimizer,
Yeah.
learning rate, I think minus LR, no?
So yeah, that's a good point. So if you think back to the gradient descent equation, the update is going to be we take the negative of the learning rate and multiply that with our derivative, and then we have that value, and then we add that on to our weight. So obviously our weight decreases. So it turns out that TensorFlow is actually going to take care of that actual operation for us. So we just pass in the learning rate that we want. Cool. So kind of the last thing that we need to do is how we discussed that TensorFlow kind of, a TensorFlow program can kind of be divided into two parts. So we've basically done with the first part, which is defining our computational graph. And now all we need to do is launch a session and then run that session and then run our optimization step a bunch of times. So yeah, how that's going to work is, okay, so the first thing that we need to do is initialize all of our variables. So we have, if you think back to our TensorFlow exercise above, we have that same init, and that's going to be tf.global variables initializer. Next, we want to launch a graph, so that's going to be that same interactive session. And then we're going to tell it to run this init operation. And then just as a sanity check to make sure I haven't made any mistakes, I'm just going to go ahead and run this. This is going to be simple. Okay, cool. And the next thing we want to do, okay, so we've initialized all of our variables. So now we actually want to launch the graph and then run the optimization step for n epochs, which was the number of iterations that we want. So does anyone have an idea basically how we're going to run this optimization step n epochs times? What's up?
Split it in a loop.
Yeah, exactly. So just put in a for loop. So we'll just go for I in range n epochs. So that'll start at 0 and go all the way up to n epochs, which I think I set at like 2500. Then essentially we're going to call a TensorFlow function to get some training data. So we do something like batch equals mnist.train. And what that does is basically, so TensorFlow, since a lot of people kind of use it for like basic experimentation like we are, it basically provides data sets and then really handy functions for accessing data. So what this is going to do is it'll look at the training data set for MNIST, and it'll give us a batch of batch size, which we specified as 128. So this batch is actually going to hold the features, so X, and then the labels Y. So that's pretty useful. And then we can actually define what we're going to run in our session. So we want to run this optimization step. So how would we run that in the session?
We have to create the session first.
So we already did that with ses equals tf.interactive session right there. So we do something like ses.run, and we have our optimizer, and then we need to feed it some data. And we have, so what do we promise to feed in? We promise to feed in some X, and we promise to feed in some Y. So we have X, and that's going to be so what that kind of does is what TensorFlow returns out of this is basically basically two objects, where the first object is going to be our features, and the second matrix is going to be our labels. So yeah, this basically feeds in our data as a dictionary. So when TensorFlow is actually evaluating this optimization step, which looks at this loss, which looks at, in this case, mean squared loss, which looks at which needs Y, and then also if you trace it back, it needs X. It'll be able to find those values and actually run the optimization step. So technically, this is all that you need to actually optimize your model. But in general, and this is good practice, as you're kind of waiting for your model to train, you want to keep track of how well it's doing. And as we kind of discussed, the loss is one way to keep track of how a model's doing. So we can basically every now and then we're going to evaluate our loss. So say every 500 iterations. So if I modulo 500 is 0, then we're going to evaluate our loss. And it's basically going to be the same predict. Yeah. And then we can just print out our loss. Cool. So essentially what we've done so far is create a session, and then using that session, we're basically running our optimizer a bunch of times, and every now and then we're printing out the loss. And back to this idea of a feed dict, we kind of have to pass in the actual training data that we're using. So basically once this loop is over, our model is going to be trained, and then we can actually evaluate the accuracy, so how well we did. And we want to evaluate the accuracy on our test data to see how well our model actually generalizes. So if you notice, we had this up here, we had this variable ac, which basically is going to give us our accuracy. So we have something like a is equal to ac.eval, and then it's kind of similar to the loss where we feed in x and y. So in this case, x is going to be our training data, which TensorFlow's MNIST library kind of specifies as the images. And y is going to be, yeah, so essentially mnist.test.images gives us the entire training data set of images. Oh yeah, sorry. mnist.test.images gives us the testing data set of images, and then mnist.test.labels gives us the testing data set of labels. So this will evaluate our accuracy across the testing data set. then we can just print that out. So now we can actually run this code, hopefully. Cool. So yeah, it's training now. Essentially, it ran like 2,500 times, and every 500 times it printed the loss. So as you can see, it didn't do too well. So the accuracy is 0.679, which is about 67.9% accuracy. So that means we found the we classified the number correctly about 68% of the time. And just kind of as a benchmark, the best networks and the best machine learning algorithms on this data set can kind of get like 99.7% accuracy. So obviously this isn't too good. So one thing we can do is, as Adit mentioned, we prefer to use a cross-entropy loss as opposed to the mean squared loss when we're doing classification. So we have, you can just change this to the cross-entropy and kind of see how that changes our loss. So let's basically just change this to cross-entropy and then run everything again. Oh, so you were right. Is it reduced? Yeah. Oh, I did that too. Oh yeah, so kind of made a mistake there. Forgot to add this reduced mean to the softmax cross entropy. So it's kind of similar to how this returned a list, and then we basically summed over the list and took the mean to be our loss. It's the same thing that we need to do here. So yeah, I just tacked on that reduced mean, and this should work correctly now. Yeah, there we go. Cool. So in that case, we get 88.9 or about 89% accuracy, which isn't great by any means, but it's a lot better. So here's kind of why we see why basically logistic regression is a linear model, and we can kind of see the limitations of linear models here, where if you think about it, there's 784 features, and we have access to 50,000 different examples. If you just do the math on that, there's basically like trillions and trillions of different combinations that our data can arrive in, and that data isn't always going to be linearly separable. So that's why in our next workshop we'll be looking at more advanced methods. But yeah, really quickly we can kind of evaluate what predictions we did correctly. So essentially, I kind of wrote this code to plot images and then take a few random images and run them through our prediction, and then we can kind of see how it does. So to go through that, we basically go through the list of random images that we have, and then we get the prediction, which is given by, again, sess.run. Cool. That should be lowercase. There we go. So these are basically what 5 randomly sampled images look like. I guess in this case we got all of them correct. So basically for this one we predicted it was a 3, the ground truth was a 3, and yeah, it's the same for the rest of them. And then we kind of just keep rerunning them with random ones. And then yeah, eventually we'll get something that's wrong or not. Yeah, I guess we do a lot better than expected. When you want your, okay, there we go. So yeah,
Yes.
this was apparent. This was predicted as a 9, and it was actually a 4. Yeah, I guess
It's a
that is a
decent
4, but
prediction.
it's a decent prediction. You can kind of see how it's a 9. So yeah, you can kind of see how our model can fail in certain cases. Yeah, that's basically all we have. Now, like, we'll take any questions you have, or yeah, we'll just be around to chat. But yeah, thank you all for coming out so much. Yeah, we do have a feedback form. Okay, cool. We do have a feedback form which we would really, really like all of you to fill out. So if you could just go to this link. And also, if you're doing that ACM membership thing, this is the event code. But yeah. Just like main thing is please fill out this feedback form because we do really value feedback. Like for example, this interactive coding thing was basically we decided to do it just because of a lot of the feedback we received. So if we keep getting more feedback, we'll be able to have better workshops. But yeah, thank you all for coming again, and yeah, see you next week.
Thank you.